Right. So we'll be continuing ahead with integration today. Okay. But just a general reminder that for the upcoming test on Sunday, the portion in integration will be only up to the basic type of integrations that we have discussed in the last lecture, and that are there in worksheet number 6. I will be sending you the full solutions of worksheet 6 also, so you should not have any difficulty with verifying your answers and going through the solutions. Okay. We will be going a little bit ahead today in integration with some more advanced techniques and also a little bit about definite integration. But this part that we're discussing in integration today will not be part of your test syllabus for Sunday. It will be there in the next test after that. Okay, so you can just mainly focus on worksheets 4, 5, and 6. Okay, and the exercise type of problems which I have prescribed in the homework assignment for this week from the modules. Okay, so those type of questions, make sure you are prepared with them for the test coming up, and you should not have any difficulty with the questions then. Okay. So let's begin by taking a quick recap of the concepts of indefinite integration that we learned in the last lecture. Okay. Right, so this is basic calculus session number 10 for us. So we are gradually coming towards the end of calculus. In another couple of weeks, we should be able to start kinematics, which will be the next chapter for us. Anyhow, so let's start with the recap of indefinite integration. So we understood that indefinite integration is an operation that calculates what is called the antiderivative. Typically, we can denote the antiderivative with the symbol I because it comes from integration for a given function. Fx. Okay. So we perform indefinite integration on the function fx, it gives us the antiderivative. And this means that if we do reverse of that, if we apply differentiation on the antiderivative, it gives us back the original function. Okay. So this is the simple definition and meaning of the term indefinite integration, and also the meaning of the term antiderivative. So we say that this quantity is the antiderivative of fx because we get it by integrating, or if we differentiate ix, we get the original function fx. And also we understood that because differentiation of a constant is equal to 0, so the indefinite integration, the antiderivative always has the constant of integration term, which is indeterminate or which is indefinite. It can be any real number constant, hence the name indefinite integration. So as a simple example, we know that, for example, differentiation of x cube is 3x squared. Okay. So that also means that differentiation of x cube plus any arbitrary constant, any indefinite constant, is also 3x squared. So that means now that integration of 3x squared will be x cube plus c. Okay. Or for example, we know that differentiation of sine x, and if we add any constant to it, is cos x. So today we will learn that integration of cos x therefore is sine x plus c. So this kind of situation is self-explanatory. It's just based on this definition that integration of a function is ix means if I differentiate that ix, I should get the original function fx. So that is the meaning of the term antiderivative, and integration is an operation which gives us the calculation of the antiderivative. Okay. So this was the definition and basic meaning of indefinite integration that we learned in the last lecture. Okay. Now, on the basis of this definition, we saw the fundamental formula for integration of algebraic x to the power n type of term. So this is given by the formula x to the power n plus 1 upon n plus 1 plus c for all n except, very important, there is the exception of n equal to minus 1. So the exception one to the above formula, we should remember along with this formula, the exception is that when we have n as minus 1, the integration is ln x plus c. So this above formula works for any power n other than -1. And when n is equal to -1, we have to use this exceptional formula, or this, you can say, this alternate formula for the exception, which is this. So then we saw that using these two formulae and the associated 2 or 3 properties, we are able to integrate any kind of simple algebraic function. Okay. So additionally, we saw properties of integration. So the first one is the integration of a constant becomes a linear term. Okay. And the second term was integration of a constant multiplied by a function can be expressed as the constant multiplied by integration of the function. And the third one was like a distributive property, that integration of the sum or difference of two functions can be expressed as the individual integrations summed or subtracted depending on whatever sign there is. So using these three properties and these two fundamental formulae above, we can see that most type of simple algebraic functions like polynomials or functions involving simple powers of x, they can be integrated very easily. Okay. So this is the part which is significant from your upcoming test point of view, the application of this formulae and these particular three properties. Okay. So let's begin today with an sort of a revision exercise of application of these. So I want you to work out these questions and send me the answers as soon as possible. I'll explain them in detail to you very soon. Okay. So this integration, then this integration, then this integration, and finally this integration.
So the first two was given in the worksheet.
Yeah, it might be a repetition of what's given in the worksheet or similar question. Okay. So anyhow, just try out the question and send me the answers. So okay, I'll put up the answers in a minute. Just try to work them out yourself. Okay. Okay, people, let's work out these questions. So I'm just step by step going to solve each of them. Okay. You can verify the answers also. So the first one, I will first have to reduce this to a power of x. Okay. Single power of x. So x to the power minus 5 by 2 dx. So now I'm ready to use this formula. So this integration will become, so don't hesitate to do the steps carefully, no matter how much time it takes, because that is the correct way to do these questions without making a mistake. So it's very easy to make a mistake with plus minus sign and all that. So that's where I would suggest that please practice these type of questions with each and every step clearly done. Now, similarly, the second one, we have to actually simplify it first so that we can express it as the sum of two simple powers. Okay. So first we can just break it like this, x by 2 plus 1 by 2x. Now we can apply the distributive property, and then also we can take the constant 1 by 2 outside in each of these integrals. And then apply the formula. So for the first one, we have this. And for the second one, remember, is the exception case, dx by x integration. It's ln x. Okay. And we can combine the constants of the two integrations and write it as a single constant. So the answer will become x square by 4 plus ln x by 2 plus c. And the good thing about integration is if you have a doubt with any of the questions, the process you have followed, you can always check your answer yourself by, you can verify your answer yourself by checking that the antiderivative indeed gives you the function by differentiation. So if you want to verify this yourself, you can just verify it this way. That differentiation of the antiderivative should give us fx. So just check this out. Okay. So differentiation of, for example, minus 2 by 3 x to the power minus 3 by 2. What it gives us, let's check. N x to the power n minus 1. So as you can see, this gives us x to the power minus 5 by 2, which is indeed this thing. Okay. So it checks out that we get. So like, given you have enough time to solve the question step by step and even verify your answer, it's actually very difficult to make a mistake in integration. You can always. Okay, now similarly, the third one, we will actually have to simplify it to make it a polynomial so that we can then apply the distributive property. If we cannot directly apply the x to the power n rule to this quadratic function to the power 2. We have to actually simplify it first. So a square plus 2ab, right, plus b square. So now it's become a polynomial. Now I can use the distributive property. Okay, so the first one, second one, and so x cube for the second one. And then the third one, and then we'll apply the formula for each one. So x to the power 5 by 5. Okay. This will become 2 times x to the power 4 by 4. So that's x to the power 4 by 2. Okay. And plus x cube by 3. And plus a combined constant of integration. So these are the answers of the first three. Okay, very good. Most of you got all these correct. Okay, now let's come to the last one. So again, it's just a matter of simplifying this. We'll have to this time simplify using the distributive property of multiplication. To express it as a sort of a function which has powers of x only. Then use the distributive property of integration. Then use the formula. So this will become x to the power 5 by 2 upon 5 by 2. So 2 by 5, okay, minus x to the power half plus 1. So that's x to the power half upon half. So that's 1 by 2. So 2 plus. Or we can also similarly express this as 2 by 5 x square root x minus 2 root x plus. So both of these are equally all right. It's just a matter of how we are expressing it finally. Okay, so hope the process is clear for each of these 4 integrations. Okay. Let me know if you have a doubt in any of the steps or anything. Right. So if you're clear with these type of applications, right, you have nothing to worry about as far as integration is concerned for the upcoming test. Okay. So plenty of questions like this in worksheet 6. Practice them out. Go through these class exercise problems also once more before the test. Okay. Even if you have any last moment doubts before the test on Sunday, you can let me know on Friday or Saturday. Just drop me a message and I'll help you out with those things. Okay. Also, like make sure you practice maxima minima very carefully. Okay. And differentiation, chain rule, and all those things. Not to mention vectors, of course. Okay. But I'm speaking from this track point of view. All right. Now we'll move ahead to the next level of applications of integration. Yes. So this is what is not coming in that test on Sunday, but this is part of overall our syllabus of integration. So we'll look at some more formulae. In particular, we'll start with the trigonometric functions. Indefinite integrations of these, or the antiderivatives. So the two basic ones are very simple to understand. Integration of sin x. It's very logical to understand that it will be minus cos x plus c, because we know that the differentiation of cos x is minus sin x. So to get rid of the minus sign, we have to transfer the minus sign this side. Okay, so differentiation of minus cos x plus, of course, any arbitrary constant will give us sin x. So there's a simple logic for this particular formula. Likewise, the second one is also very simple. We know that differentiation of sin x is cos x. So integration of cos x should just become sin x plus. Now the rest of the ones become a little bit more complicated, like integration of tan x. It is natural log of sec x plus c. Now it's easy to understand why this is the case if you just remember that differentiation of sec x is sec x tan x. So if you apply the reverse principle here, you'll see by using the chain rule, you'll see ln of something, so it's 1 upon that into the differentiation of that quantity. So differentiation of sec x is sec x tan x. Okay. Constants differentiation is of course 0. So that gives us tan x. So this is the verification of this formula. Okay. So start by just noting down these three, then we'll discuss more. The reciprocal ones we'll discuss after this. Okay, let's look at the reciprocal ones. Now these are also a little bit complicated in terms of formulae. So let's go slowly. So we'll start with cot x. So the integration of this is minus ln cosec x, which can also be written as ln sin x, because as you know that minus of ln x is the same thing as ln of x to the power minus 1. So just applying this property basically comes from this, that n times ln x is ln x to the power n. Just making use of these properties. Okay. So this also you can understand with a similar kind of verification that you've seen for tan x. In the next one, integration of sec x. Now this is ln sec x plus tan x. Okay. So this basically comes from the idea that if you differentiate sec x plus tan x, we get sec x tan x plus sec square x. That is actually sec x multiplied by sec x plus tan x. So this simple idea gives us this. Okay. So you see that if you are to differentiate ln of sec x plus tan x, Okay, we'll get 1 upon sec x plus tan x into this derivative, which we have calculated here, this term. So into sec x tan x plus sec square x. So that will ultimately give us sec x. Okay. So that is the logic of this. Okay. Oh, of course, there's a c. Don't forget the constant of integration. And somewhat similar to this sec x one is the final one, integration of cosec x is minus of ln cosec x plus cot x. Okay. So this also comes from the simple idea that differentiation of cosec plus cot is minus cosec x cot x minus cosec square x. So it is basically minus cosec x into cot x plus cosec x. So we apply this along with a similar kind of chain rule application. It's easy to understand how this formula comes. Okay. Anyway, apart from understanding the logic of the formula, main thing is you have to remember these for direct application. And in future chapters in physics, we will see that these two are of lot of importance because we're going to use these integrations in a lot of everyday applications in physics, in things like oscillations, waves, okay, circular motion, these kind of chapters. The others not so often, but once in a while. So 6 trigonometric functions, the basic trigonometric functions, antiderivatives. Right. Now the next formula we will see is for the exponential function. Now this one is extremely simple because we know derivative of exponential function is exponential function itself. So from that we can easily understand that antiderivative of e raised power x is e raised power x plus any constant, because we have seen earlier that this is a unique function that has the property that the value of the function is equal to the value of its rate of change. So that completes our list of formulae for the moment at least. Okay.
So what is the integration of ln x dx?
Yeah, good question. Integration of ln x is a little bit more complicated. integration of ln x is actually calculated by a method called integration by parts. Okay, which is, you can say, it is the equivalent of product rule. So this we'll be doing later. Okay, we'll be doing an advanced calculus. Right now we will avoid it in basic calculus. Okay.
Okay, sir.
But yeah, I mean, you can look it up in any standard textbook of class 12 maths, or but you might get confused. So let's just finish integration, basic calculus part of integration. Then maybe you can yourself, you can explore few more things in integration. When we complete this, I'll point you in the right direction for this.
Yes, sir.
Okay. Now let's see a couple of situations where we can apply indefinite integration or antiderivative constant concept to physical type of problems. Okay, so application type problems. So one of the most intuitive applications of calculus of any type, whether we are talking about integration or differentiation, is in the study of motion or kinematics. So let's see an example based on kinematics. So suppose we have a situation where a particle moves along a straight line such that it has a variable acceleration. So imagine such a situation. As you know, acceleration comes from force. So suppose some kind of force is acting on a body or on a particle which is not uniform in magnitude. The force keeps changing with time. Its direction is along a fixed axis, but its magnitude is changing with time. So then such a particle will have a variable acceleration. So suppose it has a variable acceleration given by the expression E is equal to 2 plus 2 root t, where E is acceleration in meters per second square and t is time in seconds. And it is also given to us that its initial velocity u is equal to, let us say, 4 meters per second at time t equal to 0. So now from this information we want to find out the instantaneous velocity v as a function of time. Okay. So basically this is the instantaneous velocity, you can say. So this is a typical example of the reverse process of differentiation or integration. We know that, so the concept we'll use over here, you can try this question out yourself. I'll just give you a hint that we know that instantaneous acceleration is defined as rate of change of velocity. Okay, so that means velocity should be what? It should be antiderivative of this. Okay, because E is the derivative of V with respect to time. Okay. So that means V should be the antiderivative of A with respect to time. So that's a simple logic we'll use. Okay. So now acceleration is given to us as a function of time. So we'll replace this with that function. And then additionally, there's some more information given to us that at a particular time, that is t equal to 0, the value of the velocity is 4 meters per second. So that will also get help us in finding out the one unknown quantity in antiderivative, which is the constant of integration. Remember, that's the indefinite quantity. So even that we'll be able to find out now, because in addition to this, we are also given one more piece of information that at t equal to 0, the velocity's value was 4 meters per second. So just try out this question. You will see it's an easy application of integration. Okay. This is 2 plus 2 root t. Okay, A is equal to 2 plus 2 root t. Now use the definition that A is rate of change of velocity. So that means velocity should be integration of acceleration. Okay, Kirti, your answer is correct. Very good. Anybody else has worked this out? So see, when you get the answer for v as a function of time by integrating, you can check out your answer is correct yourself, because if you differentiate that, you should come back to this value of t. So it should give you this. Okay. And if you put the value of t as 0 in this, you should get v as 4 meters per second. It's very easy to verify your answer yourself. Okay. So let's use this concept now. Okay. So A, which is dv by dt, is equal to 2 plus 2d. So this function, this is the antiderivative. This is the derivative of v. So that means v should be the antiderivative of this function. This is the logic. Okay. So basically, don't want to repeat this one. So this function, it is the derivative of v. So v should be antiderivative of that function. That's how we understand that is. Right, a combined constant. So far we are getting v, instantaneous v, as a function of time like this. But still the constant c is unknown. Okay. So for that we will use the second piece of information that is given. This one. We'll use this over here. So given that u is equal to 4 meters per second at t equal to 0. So when we substitute that here, it means that 4 is equal to 2 into 0 plus 4 by 3 into 0 plus c. So the value of c now is a known quantity. It's not any arbitrary constant. So now we have the complete answer that v as a function of time is 2t plus 4 by 3 t root t. We can write this like this also, okay, plus 4, where v is the velocity in meters per second and t is in seconds. Okay. Now you can see that this will satisfy the above two conditions which are given. If we differentiate this, we will get this. Just differentiate this, you will get this. Okay. And you can see that u is equal to 4 meters per second at t equal to 0. Yes, Anirudh, that's also correct. We can take t 2t common and write the answer that way also. That's correct. So we can express this like this also. Okay, so this is the type of application which integration can be used for. We'll do another interesting example. This is back from worksheet 2. We had done one question like this. I think it was question 4 or something, I don't remember, but it was like this, that y is a polynomial in x such that was given to us that dy by dx was a sort of a quadratic function like this, and some sets of values were given. So like this was one value given, then this was one more value given, this was one more value given, and finally one more information given was that dy by dx, this rate of change was equal to 2 at x equal to z. So from this we have to find a, b, and c. Okay. Obviously a, b, and c are constants over here, but their values are not known numerically. So at that stage, the approach that we had taken was like this, that if dy by dx is a quadratic function, then logically it means that y must be a cubic function. So we assumed that y was px cube plus 2x square plus rx plus s kind of thing, where pqrs we had to find, and from that we found abc. Okay. But now that we know integration, instead of going indirectly like this, we can go directly now, that dy by dx is this sort of function. Okay, so the derivative, so this is the derivative of y. So that means y is the antiderivative of this function. Okay. So that means y should be equal to integration of this function. So that's integration of ax square plus bx plus c, and then the unknowns can be used by can be found out by using these conditions. In that we'll substitute these conditions and we'll get the unknown quantities. So just try it out by this approach now. We'll discuss. Try to find the values of a, b, and c. Don't go back to the worksheet and check out the answers. Try to get it by this fresh approach now. Okay, yes, very good. That's correct. A is equal to 3, B is equal to 6, and C is equal to 2. And we will get Y as accordingly. So this is what our answer should be. Let's see how that works out. Okay. So we'll start with this here. Okay. This. Okay. So dy by dx was given to us as ax square plus bx plus c. Plus, let's say some constant c prime. That is the constant of integration. So we have 4 unknown quantities now. And for that, we have the 4 conditions. So we'll just substitute the 4 conditions in this equation or this equation. So from condition 1, we'll see that y equal to 0 when x is equal to 0. So this will give us this straight away. Okay. Similarly, from condition 2, we'll get that y is equal to 6 when x is equal to 1. C prime is already 0, so we'll get this additional equation. Then from condition 3, so you will get y is equal to 0 when x is equal to minus 1. So be 1 only. It's 1 square. But this will be c into minus 1 again. So we'll get the equation that minus a by 3 plus b by 2 minus c is equal to 0. So we combine these two equations. From this, we can see that by just adding them, we get b is equal to 6. And then finally use the fourth condition. So fourth condition, you have to substitute this condition here in dy by dx. So dy by dx is 2 when x is equal to 0. So this gives us directly that c is equal to 2. And then when you use this and this along with one of these equations, you can see that a as 3. You got a, you got b, you got c, and you got c prime also. So, there were few questions in worksheets 2 and 3, etc., where we sort of did an indirect application of antiderivative, where some information was given to us about rate of change. And from that, we did some guesswork about what that quantity was, so that its rate of change was like this. Now we don't need to do that guesswork anymore. We can directly operate integration and look at those type of questions in a more direct way of solving rather than that indirect guesswork way of solving. All right, so moving ahead, now we'll look at some slightly more advanced methods in integration. So we have something called integration by substitution. I was already telling you about integration by parts, but that is a bit extra advanced for basic calculus. Okay, so we will be dealing with that only in calculus of class 12th. But within our physics basic calculus, we will see this thing that we are going to do now, which is integration by substitution. So integration, and by integration we mean indefinite integration only right now. Okay. So integration by substitution is sort of the equivalent of chain rule applied to integration. So there are few different types of substitutions that we do, and like it's a matter of little bit of practice and skill to understand where what substitution is used. But the first type of substitution which we'll discuss today is pretty simple. It is substitution of a linear term. Let me explain how that works. Okay. So let's start this with an example. Then we generalize this. Suppose we have something like this: square root of 2x plus 3. We want to integrate this. Okay. Now we can see that this is basically an integration of this type, but where this quantity fx is linear. And we know that integration of root x is very simple to work out. It's 2 by 3 x to the power 3 by 2 plus c. So this is a very simple integration. So what we do when the term inside the square root is actually a linear term? So the answer to that is very simple. We substitute. So here we substitute the linear term, that is 2x plus 3, as a dummy variable, like we had done in chain rule earlier. Okay. So once we do that, this term becomes simple. It becomes root z. But of course, we cannot integrate root z with respect to x. We have to have something in terms of z in place of dx. So we have to also see the relation between dx and z. So that is very simple. Now we can see that if z is 2x plus 3, it means that rate of change of z with respect to x, derivative, that is dz by dx, is differentiation of 2x plus 3, which is just 2. So now if we cross multiply this, we can see that dx is dz by 2. So now we have the second thing substituted also. Not only we can substitute 2x plus 3 as z, but we can also substitute dx as dz by 2, and thereby we can make it an integration of this particular form, this one here. So it will become very simple. So doing this substitution in the integration now results in this, that this square root of 2x plus 3, okay, so dx integration, in this we can replace this term as square root z, and we can replace dx as dz by 2. Remember, it's no use saying root z dx, because they are two different variables. So whatever is the variable inside the square root, I have to replace dx in terms of that variable. So that's where this substitution comes in. So then the half is just a constant outside, so it's no problem. So we have root z dz, which by this formula will become, with the half outside, it will become 1 by 2 into 2 by 3 z to the power 3 by 2 plus c. Okay. And then we have to resubstitute because z was a dummy variable. So we'll do the final step as the resubstitution step. So this will become 2 and 2 cancels, 1 by 3. Now z was how much? It was 2x plus 3 to the power 3 by 2 plus c. So that becomes the antiderivative of this function. Okay. And it's very easy to verify this also. You can just differentiate and verify. Differentiation of 1 by 3 into 2x plus 3 to the power 3 by 2, we do this. 1 by 3 into, now apply chain rule, so 3 by 2, 2x plus 3 to the power 3 by 2 minus 1, okay, into differentiation of this term, so that's 2. So that's how we will get 2x plus 3 to the power half. So that's all right. Okay. That is what we should have got, so it verifies that what we've done is correct. Okay. So just go through each of these steps over here, okay, and then we will generalize this for any sort of substitution that we are doing where a linear term is substituted as a dummy variable. So we'll sort of develop a general formula for this so that we don't have to do these kind of lengthy steps every time. So go through the steps carefully. If you have any doubt, let me know. Okay, then we'll generalize this. Okay, so let's do a generalization of this now. So substitution of a linear term general formula. So suppose we know that the antiderivative of a function fx is ix. Okay. So this is known. So for example, we know that antiderivative of x square is x cubed by 3. Okay. Or we know that antiderivative of cos x is sin x plus 3. Okay. Or we know that antiderivative of e raised power x, for example, is e raised power x plus 3. Okay. Then for the integration of f of a linear term, okay, so this is a linear term because a and b are constants. What we have to do is we have to substitute that linear term as a dummy variable, okay, and then differentiate this term. So dz by dx is differentiation of ax plus b, which becomes a. So now dz by dx is a. That implies that dx is dz divided by a. So this thing and this thing can both be substituted in the original integration. So the original integration becomes, in the integration, ax plus b is replaced with z and dx is replaced with dz by a, and a being a constant, 1 by a just comes out. So now we are back to this. So from this we know that this should be equal to iz plus c, and then finally we resubstitute. We resubstitute z as ax plus b. So we get this as 1 upon a I of ax plus b plus c. So this now sort of becomes a general formula for us. We can avoid doing all these steps and directly we can use this final formula that we have got. So here we'll understand. So if we know this, so for example, integration of, let's say, 2x plus 1 whole square. We don't need to expand this and all that. Now we can just understand that it will become 2x plus 1 whole cube. Okay. 1 by a, so half into that plus. Or for example, we know that integration of cos 2x will become 1 by 2 sine 2x. Yes, because here a was equal to 2 and b was equal to 1. Here a was, b was 0. Here a was 2 and b is 1. Okay. For example, if we have e raised power, let's say 4x plus 3. So it will remain e raised power x only, but x will be replaced with 4x plus 3. And additionally, we have a 1 by b. So that's a 1 by 4 over here. Because in this case, a was 4 and b was 3. And the function was exponential. So these type of integrations now we can do directly. So just make a note of the derivation of the standard formula and these 3 examples. Then we'll do some more examples of this and you'll see this is quite easy. So this is the easiest of the various substitutions that we'll study. Okay. So while this is easy, this is also the most common type of substitution that we will come across in physics. Okay. Okay, so people hope these are quite clear. We can check out some simple examples based on this. Okay, so if you go with the direct formula method, you can see these are almost one-line solution questions. Just try to work them out. Okay. So just understand that if we know the integration of a function, if we know the antiderivative, okay, then it's very easy to integrate that function applied to a linear term. It will just become antiderivative of that linear term, but additionally divided by a, which is the coefficient of, okay, the antiderivative includes the constant of integration. So we know this, it's very easy to convert this to this. Yes. And use this formula directly.
Sir, can you scroll up just for a second?
Yeah. So any doubt in this part, Buddha?
No, sir, I just hadn't completed this
Yeah.
e power x one. Done, sir.
Done?
You can go. Yeah, thank you, sir.
Okay. Let's come to this question. Just try this out. Yes, Anirudh, that's correct. So we'll just apply this formula directly. So you can see that integration of 1 by root x is 2 root x plus c. Okay, because it will become integration of x to the power minus half. So that is, okay. So this will become 2 times square root of 5x plus 2, but then divided by 5. So 2 by 5 square root of 5x plus 2 plus c. Right. Now similarly, for the second one, we know integration of 1 by x is ln x. Okay. So making use of this, so this will become ln of 8x plus 5, but 1 by 8 plus c. Okay. Then similarly, this one will become, so integration of x to the power 3 by 2, as seen earlier today, is 2 by 5 x to the power 5 by 2 plus c. Okay. So this will become 2 by 5 into 2x plus 3 to the power 5 by 2, but then we have to also divide by another 1 by 2 because of this. Okay, become like this. And finally, this is integration of sine x, we know is minus cos x. So from that, this will become minus of cos 2x by 2. Yes. Okay, so hope all these four are clear, people.
Sir,
Yes.
so you only took the linear function and differentiated that, right?
So Kirti, a little bit louder, please, beta.
So you only took that linear function and
Ah,
differentiated that. Sorry,
yeah.
integrated that.
All of these were cases of substitution of a linear term, because they were of the integrations of were of this format that we've written about.
Yes, sir.
Of course, that might not always happen. We can have a more complicated situation where, like, for example, in the first one, inside the square root in the denominator, we need not always have a linear function. It could be something more complicated also. Like it could be, a trigonometric function inside or a quadratic function. But then for that, there's a different method. Okay, this method is only applicable when we have to substitute a linear term. Then we can use this formula directly.
Okay, sir.
Okay, so hope all these questions are clear, people. Okay. Now we'll look at a quick introduction to the second operation in integration, which is called definite integration. So definite integration results in a different type of calculation actually. It gives us a particular value which does not represent antiderivative, it represents something else. So let's understand what that is. So definite integration is an operation for calculating the area subtended by the graph of a function. Let's say y is equal to fx, okay, between what we call the limits x equal to a and x equal to b. So let's understand what area exactly we're talking about. So suppose when we plot the graph of the function y is equal to fx, the function's graph is represented by some arbitrary curve like this, let's say. Now suppose we want to calculate the area between these two limits, x equal to a and x equal to b. So that would mean that we draw this vertical line x equal to a here and this vertical line x equal to b here. So between these two limits, the area subtended by the graph or the curve of that function y equal to fx, this area is calculated by definite integration as an operation of the function fx from x equal to a to x equal to b. Okay, so this is called the lower limit and this is called the upper limit. So now this operation is represented by this symbol. We say that this definite integration is represented by a symbol like this, integration symbol of fx with respect to x, but with limits x equal to a to x equal to b. So this is what this symbol means. Symbol means this, okay? Where x equal to a, this is the lower limit, and x equal to b, this is the upper limit. So whenever we see two terms on the integration symbol, one above and one below, we understand that we are talking about definite integration. Whereas the integration symbol without any terms, without any limits, is called the indefinite integration. So this can also be just written like this, a to b fx dx. Okay. So for example, suppose we have like, let's say the graph of the function y is equal to x square, and we want to calculate this particular area from 0 to, let's say 1. We want to calculate this area. So this area will now be represented by integration of x square from the limit x equal to 0 to x equal to 1. Now how we'll execute this, we'll discuss next. Okay, but this is the definition itself, what it gives us, definite integration, and what this symbol means. It means that it is the area included by the graph of y equal to fx between the limits x equal to a to x equal to b. Okay, now next let's understand how we actually do the calculation of definite integration. So calculation of the area that is done by this operation, it is the value of the antiderivative at the upper limit minus the value of the antiderivative at the lower limit. Okay. Where this is the antiderivative of fx. Okay. So this quantity, it is the value of ix at x equal to b, upper limit, and this quantity, it is the value of the antiderivative at x equal to a, or the lower limit. So let's understand this with a simple example. So this particular one, we want to calculate this area. So integration of x squared dx from 0 to 1. So this will become what? Now we know integration of x squared dx, the antiderivative is x cubed by 3 plus c. Okay. We know this from before. So this will become the value of this function at the upper limit. So that is 1 cubed by 3 plus c minus the value of the same function at the lower limit. So that's 0. So 0 cubed by 3 plus c. So the constant cancels out, as you can see, and we get a definite value. Now this definite value is the area. This is the area. Okay. And it will be in whatever square units the graph of x and y is taken in. Suppose x and y are in millimeters, this will be 1/3 of millimeter square. If they're in centimeters, it will be 1/3 of centimeter square. Suppose x-axis is time in seconds and y-axis is, let's say, speed in meter per second, then the area will be in meters and it will represent displacement like that.
So can you please scroll up for a minute?
Sorry, beta?
So can you please scroll up for a minute?
Yeah, sure. This fine?
Yes, sir.
Yeah. So this is the important formula for us. This is how we do the calculation of the area. Okay. So in order to do the calculation, we must know the antiderivative. Without that, we can't calculate.
So,
Yeah.
sir, can you also please discuss the last question of the first major test after this lecture?
Sorry, the last section of.
Last question of the first major test of physics.
Okay. I'll go back to that. Okay. Let's just do one more example first. Okay. So now, for example, let's calculate this thing. Cos x integration from x equal to, let us say, pi by 6 to x equal to pi by 2. So let's work out how much this is. Okay. So while you're working this out, I'll just show you what this means on the graph. So as you know, the graph of y is equal to cos x is a shape like this, right? It's like this. So pi by 6 would be somewhere here, let's say. So what we mean by this is actually this area. This area would be represented by this integral. Now we will just use this fact that integration of cos x, the indefinite integration, is sin x plus c, right? So limits a to b cos x will simply become sin b minus sin b. The constant term anyway cancels out, right? So you can see that this will become minus, so that's sin 90, which is 1, and sin 30, which is half. So this will be half or 0.5. So this will be this area. Okay, so hope this example is clear to all of you.
Yes, sir.
Right. So with this, we complete today's lesson. Yeah, you wanted to see the first page, is it? One of these questions, or anyhow, so I'll send you the notes. You can pick it up from there. Okay. So that's it for today's session. Wish you all the best and thanks for attending. Work hard over the next couple of days revising for your upcoming test and all. Okay. If you have any last moment doubts by Friday or Saturday, do message me or contact me. I will help you out with that. Okay. All the best for the test coming up. Have a nice day.
So,
So,
Yes.
also, as I said before, can you please solve the last question of the first major test from physics?
Last question of the.
First major test of physics.
Okay. Can you tell me the question, Beta?
1 second, I'll just open that.
Or Anirudh, just do one thing. Na? Just send me the question on WhatsApp later. Na? I'll send you a print of how to solve it. Okay.
Okay, sir.
Okay.